we were discussing the phasor diagrams of a single phase transformer at no load and full load, and we have considered uh, the ideal transformer first. Now, why we have considered the ideal transformer first? Ideal transformer is considered first to explain uh, or to get an easier explanation of what happens in a transformer. Okay, so that is why uh, first of all it is assumed that there will be no winding resistances, then no core loss, no leakage flux, and the magnetization curve for the transformer is linear. Okay, so these four assumptions are actually for an ideal transformer which is not having any imperfections. Okay, so ideal transformer means perfect transformer. No winding resistance means no copper loss, no leakage flux means there will be no voltage drop due to this leakage reactance, then no core loss, that means the there will be no loss inside the core, and the magnetization curve that is linear. Okay, so now the if the magnetization curve is not linear, then it will introduce harmonics in the voltage waveform. Harmonics means voltages which are frequencies having frequencies which are multiple of the fundamental frequency. Okay, harmonics means there will be one fundamental frequency, that is 50 hertz frequency voltage, and with that fundamental frequency voltage there will be some other voltages also which will have the frequencies in multiples of the fundamental frequency. Okay, so now if we want to draw phasor diagram or equivalent circuit, then all the parameters for all the quantities must have the same frequency, which means for every frequency voltage we will have one phasor diagram. Okay, so that is why to avoid such complications in your syllabus, only this 50 hertz frequency quantities are considered. So we will consider the that means this assumption, that is the magnetization characteristic of single phase transformer is linear, that will remain same, but the other imperfections in case of practical transformer that we will introduce one by one. Okay, so let us consider the transformer phasor diagram, I mean the practical transformer phasor diagram at no load condition first. So this phasor diagram is of a practical transformer which will have those imperfections except the non-linearity of magnetization curve. Okay, so first of all, how to draw the phasor diagram? The same notation we will follow, or convention, that is mutual flux is common to both the primary and secondary. So we will consider it as the reference phasor. The induced EMFs E1 and E2 lag this flux by an angle of 90°. Then the voltage minus of E1 is replaced by V1 dash, and this V1 dash may be treated as a voltage drop in the primary in the direction of primary current. Okay, so now we have a new term V1 dash. This is not the supply voltage or the applied voltage V1. This voltage V1 dash is equal to the primary induced EMF E1 but in opposite direction. Okay, if we consider the schematic diagram, we can see this is the supply voltage V1, this is the primary current I1, then E1 is here, which is opposite to that of V1, and but as we are having some voltage drop due to this winding resistance and leakage reactance, so V1 is not equal to E1. There has to be some other voltage which is equal to E1, so that voltage is denoted by V1 dash, which is equal to E1 but in opposite direction as per Lenge's law. Okay, so that is why we require this new term V1 dash. Now let us consider the effect of iron loss first. Effect of iron loss means core loss. So there are two types of core losses: eddy current loss and hysteresis loss. Okay, so let us see. The current in the primary is alternating in nature, we know that. So this is the waveform of alternating current. So when this current flows through the primary winding, it will magnetize the core over which this primary winding is wounded. Okay, so now we know the equation H equal to N I by L. So N is number of turns, length is main part of the flux, and I is the current. Okay, so if I is sinusoidal in nature, then this H is also sinusoidal in nature. Okay, so when I varies sinusoidally, this H will also vary sinusoidally. Okay, so initially I is 0, so it will start from this point and reach this point, so that, and now that means it will saturate the core. Then if so this is the maximum point, so at this point then it will start reducing, then it will follow this path, and at this point the value of magnetic flux is V and the current value is 0 at this point. Then it will start increasing in the negative direction. So after some value, this we will get the flux point, I mean flux value 0, but the value of current at that point is having some negative value. Then it will increase further. So at this, in this, following this line, we'll have the maximum value of H, then that is the saturation point. Again it will start increasing, so we will follow this line. Okay, so my point is, at this point and at this point the value of current is 0, but the value of H is not 0. What is the meaning of this? The meaning is the flux value will lag the current value by some angle. Okay, here current is 0 but flux is not 0. Here current is 0, current is having negative value but flux is only 0. So this flux value always lags the current. Is it clear up to this? Hello?
Yes, sir.
Yes.
Yes, sir.
So here the current, that is the exciting current, is not exactly in phase with the flux. Okay, due to this hysteresis loop, there is some phase angle difference between the current wave and the flux wave. Okay, so the point is, at this point the current value is having positive magnitude but the flux is 0. At this point current is maximum but the flux is not maximum, it is still increasing in nature. So after certain time interval the flux value is negative, maximum positive, but the current is decreasing. Okay, it has already crossed its maximum value. So there is always some phase angle difference due to this hysteresis. Okay, so this exciting current leads the flux by some angle, and that angle is known as the hysteretic angle. So let us consider that angle as alpha. So this angle is known as the hysteretic angle. Okay, here this angle is the angle alpha, which is known as the hysteretic angle. So we previously we have seen that for a ideal transformer, the phase the two phases, flux and the exciting current, are in same phase. So that is not true for a practical transformer. So there is a phase angle difference between this exciting current and the flux waveform. Okay, so the no load current IE is called the exciting current of transformer and can be resolved into two components. See here, this is the exciting current which leads the flux phi m by an angle alpha. Okay, so for practical transformer, IE and phi m are not in phase. Now since it leads the flux phasor by an angle of alpha, so with respect to this reference phasor, we can resolve this exciting current into two components, one along the flux phasor, another along the line which is in quadrature with the flux phasor. So this is one component Im, and this is another component IC. This component which is in phase with flux phasor is called the reactive or the magnetizing current of magnetizing current. That means the component which is in phase with flux phasor is the reactive or magnetizing current component, and it is the component which is responsible for the production of flux phi. So that means Im will produce the flux phi. Okay, exciting current IE is having two components, one is Im, another is IC. So Im which is in phase with phi m, that will produce the flux phi m. So then what is the other component? The other component IC is called the core loss component of flux, and it is in phase with V1 dash, and this component is actually responsible for the core loss PC, which is the sum of total hysteresis loss as well as eddy current loss. Okay, so core loss component is IC, and this is in phase with V1 dash but in quadrature with flux phasor phi m. Hello, any question?
Yes, sir. Sir,
Yes,
what is the B1 dash, sir?
please repeat. Your voice is breaking and you are.
Sir, please explain that B1 dash.
Okay, that I will explain once again. See this schematic diagram. Here V1 is the supply voltage and E1 is the induced EMF across the primary winding. So what is this V1 dash? Okay, see, as this is a practical transformer, so there will be some winding resistance in the primary winding. So R1 is the primary winding resistance and X1, that is the primary leakage reactance. So primary leakage impedance is Z1, which is R1 plus JX1. Okay, so when V1 is applied across this primary winding, you have to subtract this impedance drop, that means V1 minus I1 into Z1, then you will get some voltage. Okay, some voltage.
Sir, got it.
Okay, so what is this voltage? This voltage is V1 dash. We denote it by the V1 dash, and this V1 dash is equal and opposite to that of E1. Okay, is it clear?
Yes, sir, got it.
Okay. So exciting current has two components. One is magnetizing component, another is core loss component. Magnetizing component is in phase with flux, and the core loss component is in quadrature with flux, and which means it is in phase with V1 dash. Okay, so how to calculate this core loss? We can multiply this V1 dash and IC to get the core loss. So therefore V1 dash IC is equal to PC, or IC equals to PC by V1 dash. So IC is the core loss component of current, and now we can write this equation, that is IE is equals to IC plus IM. So exciting current is the phasor sum of IC and IM. We can also see from the phasor diagram that IM and IC, the resultant of these two currents, is equal to total exciting current IE. Now at no load condition, this exciting current is the only primary current, because there is no load component of primary current, because it is the transformer is running under no load condition, so no secondary current, that is I2, and there will be no reflection in the primary side. Okay, so IE, that means the exciting current, is the only primary current for any transformer under no load condition. And this exciting current has two components. One is magnetizing current, which is in phase with flux. Another is core loss component, which is in phase with V1 dash. Okay, clear up to this?
Yes, sir.
Any question? Anyone? Now the effect of transformer resistance. This is very simple. Since the windings are made up of some conducting material, so there has to be some resistance, and by adding the voltage drop due to this winding resistance to V1 dash, we will get actually we have to add all the voltage drops, not only the resistive drop. So here in the phasor diagram, this voltage drop R1IE, that is the primary winding resistive drop, this drop is added with the voltage phasor V1 dash. Okay, so why it is drawn in parallel with the current I? See, this line and this line are in parallel. So because we know that the resistive voltage drop and the current will be in same phase. So actually this I and R1 I, they are in same phase. That is why this drop is added to V1 dash and drawing it in parallel with I. Okay. So R1 I is in phase with I and is drawn parallel to I in the phasor diagram. So that is the effect of primary winding resistance. Now the effect of leakage flux. So now I am going to discuss this leakage flux in more details. So what is this leakage flux? In this diagram you can see a schematic of a transformer under no load condition, and this phi L1 and phi L1, this flux and this flux. These two flux lines are produced by the primary winding and linking with the primary winding only. They are not linking with the secondary winding. That is why these two flux lines, that means this flux phi L1 is called the leakage flux. Any flux which is produced by any winding and linking with the same winding also only, and it is not linking with any other winding, then it is called the leakage flux. Here in iron core transformer, most of the flux is confined to high permeability core. That means the maximum amount of flux produced by this primary winding remains confined within this core. So that is the mutual flux phi. But there is some flux which will not link with the secondary coil, or it is not confined within the ferromagnetic core. So these flux lines are called leakage flux. Okay, so there will be some leakage. Now we have to understand the behavior of this leakage flux. See, from the diagram we can see the mutual flux, this phi, it is confined within the ferromagnetic core. So it will magnetize the ferromagnetic core, and depending on the value of this flux, this core will saturate. That means there will be some hysteresis loop. Okay, and this flux will link with both the windings. So these are the properties of this mutual flux phi. Now consider the leakage flux. So the properties of leakage flux will be a little bit different from the mutual flux. First of all, from this diagram we can see this flux is produced by primary winding. I mean this phi L1 is produced by primary winding and it is linking with primary winding only. It is not linking with the secondary winding. So this is the first difference from that of mutual flux phi. Second difference is that the path of the mutual flux is within the core only, but the path of the mutual leakage flux phi L1 is some portion it is through the core and the maximum portion is through the air, isn't it? It will complete its path through core and then through air. Okay, so then what will happen? That means the that means the since this mutual flux is mutual flux is involved with some hysteresis loop, that is why this exciting current leads the mutual flux by some hysteretic angle. And now the leakage flux, since its path is mostly through air and it is very difficult to saturate the air, therefore there will be no saturation. As there is no saturation, there will be no hysteresis. That means the flux, that means BH curve for this leakage flux will be like this. It will rise in this way, and then if we reduce the current and when it gets reversed in the reverse direction, then it will get in this way. So its path is linear. So this is BH curve for phi L. Okay, so it does not involve with any hysteresis loop, which means this flux is in phase with the exciting current. Is it clear?
Yes,
Since
sir.
since the path of leakage flux is mainly through air, therefore the reluctance offered by the air to phi L1 is due to air only. So it is very difficult to saturate air, and therefore it does not involve with any hysteresis loop, and therefore this phi L1, this flux, is in phase with the phase with the exciting current IE. So that is the behavioral difference between phi L1, I mean this leakage flux produced by primary winding, and the mutual flux phi. Mutual flux involves with some hysteresis loop, therefore it lags the exciting current by some angle, that is the hysteretic angle alpha, but phi L1 does not involve any hysteresis loop, therefore it is in phase with the exciting current IE. Okay, so in this diagram we can see this is the exciting current IE phasor and this is the phi L1 phasor. So that is the leakage flux phasor. Now you know any flux when links with any coil, any alternating flux obviously links with any coil, there will be some induced EMF. So this phi L1 will produce its own EMF which will lag this flux by an angle of 90 degree. So EX1, this voltage, induced voltage, is due to this phi L1. So this phasor which is lagging phi L1 by an angle of 90 degree. So EX1 is the voltage due to phi L1. This voltage lags the flux by an angle of 90 degree. Okay. Is it clear up to this?
Yes, sir.
Okay. Now this EX1, this is a voltage, as I have mentioned that you can add similar quantities using this phasor notation. Okay, so voltage you can add, but voltage current you cannot add. So EX1 is a voltage, so that voltage you can add with another voltage. So here we have V1 dash, with it we have already added this voltage drop IR1. So we have to add this voltage EX1 with this R1 IE. But see here, from at this point this EX1 is opposite in direction. So you cannot add it here. So you have to take the negative of this. So that is why this EX1 is considered as a voltage drop due to some reactive component. Why reactive? Because this voltage drop is in quadrature with resistive drop. Recall the voltage triangle for an RL circuit. So this is VR, which is equals to I into R. This voltage is VL, which is I into XL, and this is the supply voltage V, which is equal to I into Z. Okay, so since this VL is in quadrature with VR, so this from this we can conclude that this VL is reactive in nature. So we can see from here that EX1 is in quadrature with R1IE, so it has to be some reactive voltage drop. So we can write it as IEX1, and to add it with R1IE to get V1 we have taken negative. So here JX1IE, that means the reverse of EX1 is equal to JX1IE. So this is a voltage drop. So this X1 is called the leakage reactance. Since there is no physical existence of EX1, this is a fictitious quantity, but since this voltage drop due to this leakage flux is reactive in nature, so we are considering it as the product of this exciting current, I mean the current flowing through this winding, and some reactance value. So for primary it is denoted by the symbol X1. Is it clear up to this?
Yes,
Sure.
sir.
So we can write EX1 equals to minus of JIEX1, and to add it with R1IE we have taken its opposite, I mean this reverse phasor to get the supply voltage V1. So if we as it is a reactive voltage drop, since it is in quadrature with resistive voltage drop, so we can write this IEX1. So here X1 is having the nature of some reactance, and it is called the primary leakage reactance. So X1 is the primary leakage reactance. So if we complete this triangle, we will get IZ1. Okay, IEZ1. So V1 dash plus IEZ1 will give you the supply voltage V. Hence X1 is a fictitious quantity that I have already mentioned. So total voltage drop in the primary at no load is IE into R1 plus JX1, which is equals to IEZ1, where Z1 is called the primary leakage impedance. Therefore, the primary voltage equation at no load can be written like this: V1 is equal to V1 dash plus I into R1 plus JX1. That means, as I have already written, this after subtracting this voltage drop, leakage impedance drop from V1, you will get the V1 dash, which is nothing but uh, a voltage which can be considered as a voltage drop along the direction of flow of primary current, which is exactly equal but in opposite direction to that induced EMF across the primary winding. So V1 dash is actually does not exist across the primary winding of primary winding. As per Lenge's law, we have considered some voltage which is denoted by the symbol V1 dash. Okay, so E1 is actually the induced EMF across the primary winding, V1 dash is a voltage which is considered as a voltage drop in the direction of current flow in the primary winding, and V1 dash is equal but in opposite direction to that of E1 as per Lentz's law. So the primary voltage equation at no load condition is given by equation number 16. Is it clear up to this?
Yes, sir.
Yes, sir.
So for practical transformer, there will be some winding resistance R1, there will be some leakage reactance X1, and there will be some core loss, and due to that core loss, we will have one component of current, of exciting current, that is IC. So these are the corrections for those imperfections in a practical transformer. Now under loaded condition, see, when this switch is closed, there will be a current flowing through the secondary winding, and we have already seen that due to the presence of this current, the primary current will increase from I to I1. So now this I1 is having two components. One is I1 dash, that is the load component of primary current. Another is IE. This I remains fixed. Depending on the value of I2, this I1 dash will change. So as a result, the total I1 will change. Okay. Now since there is some current flowing through the primary winding, so it will produce its own MMF, and it will produce its own flux also. That flux is demagnetizing in nature to that of mutual flux, and also there will be some leakage flux in the secondary side also. Okay, so that leakage flux is phi L2, and the behavior of this phi L2 and phi L1 are similar. It does not involve with any hysteresis loop because its path is through air mainly, and hence this phi L2 will produce its own induced EMF, which can be treated as the reactive voltage, and we will have the secondary leakage reactance as X2. Okay, and the secondary winding will also have some resistance, so that is R2. Okay, so therefore we can draw the phasor diagram under loaded condition considering these new parameters or new conditions. So when in figure 1, when switch S is closed, I2 starts flowing through the load as well as through the winding. Let us assume that this load is inductive in nature. So I2 sorry lags the load voltage by an angle of theta 2, and the secondary MMF I2 and 2 gives rise to leakage flux phi L2, which links only the secondary winding and not the primary winding. So this is the complete phasor diagram of a practical transformer under loaded condition. Okay, so from no load phasor diagram, we already have this phasor phi m, IA, IE, IC, V1 dash, this one, and this one. Okay, E1 and E2 also. So now we have to draw the other quantities. So first of all, draw I2 and V2. I2 will lag V2 by an angle of theta 2. So here V2 and I2 are drawn, and the angle between V2 and I2 is theta 2. Okay. Now in parallel with I2, draw I2 R2. This line and this line are in parallel. Then draw I2 X2, Ji2 X2 in quadrature with I2 R2, and complete this triangle then you will get the secondary induced EMF E2. Okay, so this line is in parallel with I2, this line is in quadrature with I2. Now draw I1 dash in phase of opposition to that of I2. So this is the load component of primary current. Find the resultant of IE and I1 dash. IE and I1 dash. Then you will get the primary current I1. Now see this triangle you have to modify as per I1. Previously it was IER1, IEX1 because there was no load component. The exciting current was the only primary current. Here this now the total primary current is I1, so you have to draw I1R1 in parallel with this line, and this I1 JI1X1 in quadrature with this line. Okay, that means the total primary current. Then you can add this point and this point to get the total supply voltage. And the concept of this X2 will arise from the same following the same procedure. That means you have to consider phi L2 in phase with I2, and with this phi L2 there will be some induced EMF lagging it by an angle of 90 degrees. So EX2, so again EX2 can be expressed as minus of JI2X2, which you have to draw here. Okay, now if you are asked to draw the phasor diagram of a practical transformer, you don't have to draw this phi L2 and this line, you can directly draw this line. Okay, so you have to show phi M, IM, IE, IC, then I1 dash I2, V2, these two voltage drops, and then two induced EMFs, and in the primary side V1 dash equals to minus of E1, then I1 R1, JI1 X1 and V1. Now, this part you don't have to draw, this is for understanding only. Okay, so how to draw this phasor diagram, total phasor diagram? First of all, take the mutual flux as the common as the reference phasor because it is common to both primary and secondary quantities. Induced EMFs E1 E2 lags phi by an angle of 90 degrees. So first of all draw phi, then E1 E2 lagging phi by an angle of 90 degree. Then exciting current IE equal to IC plus IM. So draw IE leading phi m by an angle of alpha, and then resolve this IE into two components, one along phi, another along V1 dash, that means in quadrature with phi m. So the component IM is in phase with phi m and component IC is in quadrature with phi m. The effect of secondary leakage flux is represented by another reactance X2. So the secondary voltage equation becomes this: E2 is equals to V2 plus I2 into R2 plus JX2, that is I2 into Z2. Okay, so Z2 is the secondary leakage impedance. And I1 dash is the primary load component of primary current. So total primary current is I1 equals to I1 dash plus IE, that means the phasor sum of I1 dash and IE. The voltage V1 dash equal to E1 is considered in the direction of current in primary winding. So V1 dash is equals to minus of E1. The drop in the primary is I1 into R1 plus JX1. So now the primary voltage equation modifies to this. Initially it was under no load condition, it was V1 equals to V1 dash plus I into R1 plus JX1. So now this current is I1, not IE. So that's all about this phasor diagram of a single phase transformer. Now this phasor diagram is for lagging power factor. You practice drawing this phasor diagram at UPF, that means unity power factor, and leading power factor, that means for resistive load and capacitive load. Any question?
Sir,
Yes.
if you want to draw phi L1, then it would be along I1, not IE, not IE.
No, it is along IE.
But sir, after
Oh,
under
sorry,
load,
yes. If you want to draw phi L1 in this diagram, you have to draw it along phi, I1. You don't have to draw that part. You have to show only the main quantities. Okay, as you are you have already shown this x1 and x2, so you don't have to draw this phi L1 and phi L2. Any other question? Okay, then time is over. So today up to this.
Hello, sir.
Just a minute.